Hello everyone, my name is Chuan. Today Xiao and I will be presenting the paper named Automatic Table Union Search with Tabular Representation Learning, which is published in ACL 2023. With the growth in the volume of open datasets from governments, academic institutions, and companies, there's a surge of demand for discovering related tables from data lakes. These related tables are useful to many data analytics and machine learning tasks. Table union search is one of the critical tasks in data discovery over data lakes. The goal is to find tables from a data lake that are unionable with a given query. With two columns from two tables, we say these two columns are column unionable if they are semantically equivalent. Building on top of the unionable column definition, we consider two tables are unionable if there exists at least one unionable column pair where two columns are from two tables. Formally, the problem we study in this work is top K table unionable search. The inputs are a query table and a data lake with a large collection of tables. The expected output is top K tables from the data lake with the highest probability to be unionable with the query table. The table union search problem has been studied previously. In the original table union search paper, the authors ensembled three signals for finding unionable tables. Specifically, the system relies on overlapping values between two columns, mapping columns to possible class labels in an ontology, and also column embedding similarity based on pre-trained word embeddings such as glove. D3L is another work, aggregates different types of similarity scores in a weighted manner. Specifically, it uses similarity of column names based on qgrams, Jacquard similarity of infrequent token sets, value embedding similarity of frequent token sets, Jacquard similarity of regular expression that generate values of two columns, as well as distribution similarity of numerical values. More recently, CentOS is designed to identify tables that share unionable columns and relationships by leveraging external and self-curated knowledge bases. However, all these methods have some limitations, such as the dependencies on handcrafted features or embeddings generated by language models. However, the representations here may not fully capture the column semantics. They also tend to ignore the contextual information within the table and the intrinsic semantic relation signals between column pairs, which could be beneficial for learning a more semantic aware representation of each column. Another way to look at existing work is that they're pretty much all models capture the column relations as a scalar, whereas our method models the column relation as a vector. Our proposed method, AutoTUS, consists of three major components: table union, table noise generation, multi-stage self-supervised column relational representation learning, and table unionable score. We first introduced the table noise generation process in the training stage. The goal here is to better imitate the data distribution in real world by introducing noise to both table schema and value instances. Here are some examples of the noise to column names. We can randomly drop prefix or abbreviate the column names. We also use synonym substitutions or acronym in column names. Regarding noise in column values, we replace or insert characters with proximal characters. We can also delete or repeat characters. And lastly, we change the numeric column formatting.
The second main component in our proposal is multi-stage self-supervised column relational representation learning. It aims to extract column relation as column relational representation, which is learned from iterating over multiple stages. This main component consists of 3 subcomponents, that is a contextualized column relation encoder and 2 updaters. Specifically, the encoder serialized and tokenized the column relations as the input and leveraged the BERT to generate contextualized column relations or column pair embeddings. The first updater optimizes the encoder through a relaxed constraint by performing clustering over the column pairs. The second updater uses the generated pseudolabel, which is the membership of the pair to the clusters, to further update the encoder with a more strict constraint by performing a classification task. The clustering and classifications are performed in a bootstrap loop that iteratively improve the language model to generate a better column representation. The intuition behind this approach is that the clustering classifications can be seen as a process of identifying hidden semantic type of the column pairs. Performing such auxiliary tasks lead to a better table encoder for the table union search task. Let's take a closer look at these subcomponents. In a contextualized column relation encoder, we use BERT to encode the column pairs. Columns in a real-world table may contain thousands of tokens, and randomly discarding tokens will lead to a loss of important semantics. Therefore, in this work, we score the importance of each token or cell in a column and keep cells based on their importance. More specifically, we adopt TF-IDF score to calculate the token importance, and the cell score is calculated by averaging the TF-IDF of all tokens within the cell. The selection is then made until the total token count reaches the input budget. The details about how we serialize a column for BERT can be found in the paper. After the column pair embeddings are generated by the encoder, the first updater computes K cluster centroids and softly assigns these embeddings to K clusters. Specifically, we define a similarity functions to calculate the distances from a column pair embedding to all K centroids. These distances together can be seen as assignment probability distributions for a column pair over the clusters. On the other hand, we leverage a target distribution definitions from the literature, which estimates the ideal case. With these two distributions, we can then measure the KL divergence loss as a supervisions to update the encoder. The optimizations from the last step can be seen as a soft constraint when updating the encoder, where we use soft cluster assignments. In this step, we perform classifications on the column pair embedding and force the model to pick one cluster. The label is obtained from the clustering step. The loss between the predicted class and the ground truth label is then used to further update the encoder. After this step, the embeddings are then regenerated using the updated encoder, and it goes another round of clustering and classification. This loop is executed multiple rounds until convergence. Next up is the last main component, table unionability score. This component basically computes the table unionability score between the query table and a table in the data lake, based on the column representation generated by the encoder. The idea here is to score the unionability by counting the unionable column pairs between the two evaluated tables. Specifically, instead of computing the similarity between two column embedding, such as cosine similarity score, we leverage the classifier to predict the class, which represents a hidden unionable semantics. The score is basically computed by dividing M, which is the count of the majority class, by N, which is the number of column pairs between the two tables. To evaluate our technique, 3 public datasets are used, Santos, QS small, and QS large. These 3 datasets are subsets of open data from US open data, UK open data, and Canada open data, with manually labeled data. These data are filtered to remove a lot of table noise to maintain high quality. In order to verify the robustness of the model, we synthesize a test set with table noise. In order to verify the robustness of the model, we synthesize a test set with table noise. We added both column value and column name noises to the tabular data and obtained the synthesized CentOS and TOS large. We compare AutoTOS with baseline models in two categories. The first category is table union search model that adopts various column features to calculate the table unionability score. Here we have D3L, SATL, StarMe, and CentOS. The second category is table pre-trained model that leverages unlabeled tables for self-supervised pre-training and achieve promising results in various table-related NLP tasks. Here we have TabBERT, TABI, Tuta, FORAP, and TableFormer to calculate the column unionability. This table shows the average results on 5 table union search benchmarks. The proposed AutoTOS consistently outperforms all baselines in mean average position and recall. AutoTOS on average achieves 5.1% higher MAP and 3.1% higher recall across various benchmarks. The table union search baselines can achieve better results than the table pre-trained baseline by optimizing the column representations specific to the table union search task. AutoTOS exploits the column relational representation and is able to beat all the table union search baselines. In addition, we study the performance changes brought by using larger base encoders, BERT large and Roberta large. We concluded that leveraging a large-scale pre-trained language model with more parameters can lead to a better MAP and recall. BERT large and Roberta large obtain an average boost of 1.1% and 1.4% respectively. We also conducted ablation studies to show the effectiveness of 3 different modules of AutoTOS, which are table noise generator, updater via clustering, and updater via classification. The general conclusion from ablation study results show in this table is that all 3 modules contribute positively to improve the performance. We also investigated the effect of table noise in column value and column name. We observed that adding table noise to both column value and column name generally help improve the performance, whereas changing column name has a slightly larger effect. These improvements may be related to the fact that column name summarizes the entire column semantic. So adding noise to the column names can make the model more robust to table noise and thus obtain more performance gains. However, adding more noise did not consistently improve the performance, suggesting that the model needs to find a trade-off between noisy data interpretations and increased robustness to the noise. In this paper, we propose a multi-stage self-supervised table union search framework, which represents column relation as column relational representations and learn this representation in a multi-stage manner that can better describe column relation for unionability prediction. In addition, a table noise generator is proposed to improve the robustness of our approach against the table noise. The conducted experiments demonstrate the effectiveness of the proposed approach.